So, good morning, everyone. Respected dignitaries, Honorable Vice Chancellor, MIT University, Punjab, Professor R.K. Kohli, registrars, deans, fellow colleagues, respected guests, and dear students. Today, we all are gathered here to celebrate National Mathematics Day, a day of significance in the world of numbers and equations. It marks the birth anniversary of the legendary Indian mathematician Srinivasa Ramanujan, who was born on December 22, 1887. We pay tribute to the man whose contributions to the field of mathematics were nothing short of extraordinary. Srinivasa Ramanujan, a self-taught mathematician, genius, left an indelible mark on the world of mathematics with his profound insights, deep theorems, and a unique approach to numbers. I feel privileged to have with us Dr. Apoorva Khare, Associate Professor, Indian Institute of Science, a great Indian mathematician and scientist who has received various awards, including the prestigious Shanti Swaroop Bhatnagar Prize for Science and Technology, the highest science award in India for the year 2022 in mathematical sciences. Dr. Khare works in matrix positivity and analysis, discrete mathematics, and representation theory. Dr. Khare obtained his bachelor's in statistics in the year 2000 from the Indian Statistical Institute at Kolkata and his PhD in 2006 in mathematics from the University of Chicago. He then held various postdoctoral positions at the University of California at Riverside and Yale University, and a research associateship at Stanford University before joining the Indian Institute of Science in Bangalore. Besides the Bhatnagar Award, Dr. Khare is also the recipient of Swarn Jayanti Fellowship and Ramanujan Fellowship from SERB DST, Government of India, and a Fellow of the Indian Academy of Sciences, besides many other awards. In a publication by the Government of India celebrating 75 years of Indian independence, Dr. Khare was listed as one of the 75 scientists aged under 50 who are shaping today's India. Before I invite Professor Khare to give his talk, I would like to extend a warm welcome to our esteemed guest of honor, Dr. Arun Kumar Grover, Fellow of the Indian Academy of Sciences, Bangalore and Allahabad, physicist, and former Vice Chancellor of Punjab University, to kindly say a few words. Welcome, Professor Grover.
Good morning, all. I am very happy to greet all of you on behalf of President of Society for Promotion of Science and Technology in India, who incidentally is not with us today, but he is a very passionate mathematician. He founded this society in the year 2009, the birth centenary year of Homi Bhabha. So Mr. Dharamveer, who had his undergraduate education at IIT Kharagpur and postgraduate education at IIT Kanpur, later on had joined Indian Administrative Service. And while he was superannuating as the Chief Secretary from Government of Haryana, he thought of creating this society in partnership with his wife, who was a professor of physics at Punjab University, K.R. Dharamveer. So I was a part of the Homi Bhabha birth centenary commemoration at Tata Institute of Fundamental Research, an institute founded by Homi Bhabha. So lo and behold, Homi Bhabha had thought of initially starting Tata Institute of Fundamental Research as an institute for physics. But before the institute commenced operations, Paul Dirac, whom Bhabha admired, he had advised Bhabha that the mathematics should be included in an institute for fundamental research. So the name was changed from Tata Institute of Fundamental Research in Physics to Tata Institute of Fundamental Research per se, as the institute moved from Indian Institute of Science, Bangalore to Bombay on 19th of December, 1945. So mathematics and physics grew up together at TIFR. It became the cradle of the atomic energy program. And as the time went by, the School of Mathematics of TIFR actually became more famous than the School of Physics of TIFR. So National Board for Higher Mathematics, which coordinates all these mathematics activities, which nurtures young mathematicians in India, is a creation of School of Mathematics of TIFR. So it's the National Board of Higher Mathematics which assumes responsibility of reaching out to young students in school, change the curricula of school, mathematics in school, etc., etc. And at some stage, started to identify young people from schools for participation in the National Mathematics Olympiad movements. Our speaker today, Professor Avinash Khare, has gone through all those stages. I got associated with this Olympiad movement, not in the field of mathematics, but in all other disciplines of science. In the year 2002, when Srimati Sudhamurthy, one of the founders of Infosys, she gave an endowment to award the Indian medalists in the Olympiad competitions every year. So we started to get all these medalists together once in a year in the month of December at Homi Bhabha Center for Science Education. And we used to hold these expository lectures for all the people who made it to the the last camp of the Olympiad movement. The students, their teachers used to be got together for a day in Homi Bhabha Center for Science Education. When all this process was going on, Professor M.S. Raghunathan said, this event should be organized every year on 22nd of December, on the day of birthday of Ramanujan. So we started to do it on December 22nd every year. And lo and behold, in the year 2012, the government of India accepted to declare December 22 as a National Mathematics Day. So from then onwards, this National Mathematics Day is commemorated all across India, not just the Homi Bhabha Center of Science Education, which was doing it a few years before that. So I'm very happy that after I superannuated as a Vice Chancellor of Punjab University, Professor IBS Pasi, who was one of the founder members of ISA Mohali, and also the president of the National Academy of Sciences of India, and also the founder, vice president of the Society for Promotion of Science and Technology in India. He called me one day and said, I have done it for so many years, so please take it over from me and have this day commemorated every year on behalf of National Academy of Sciences of India, Society for Promotion of Science and Technology in India, and for all the academic institutions in our region. So for the last 5 years, 4 years, I am doing this, but last 3 years have been the pandemic years. But this is the first time we are commemorating the National Mathematics Day in a physical form with all of you occupying this auditorium. And this lecture is also going to be broadcast to anyone else who chooses to join us offline. So it's in a hybrid mode. We have a wonderful speaker today. SPST is very, really proud and privileged to have someone of the stature of Apoorva Khare to give this talk. We have SPSTI has organized a mathematics lecture in this form in a big hall once earlier. I was present there. That lecture was given by Professor Dinesh Singh, the former Vice Chancellor of Delhi University. The lecture was in a Tagore Theatre. The hall was full like we have it today. And in fact, photograph of that lecture is advertised by SPSTI on its pamphlet. So maybe we will change that photograph with Apoorva's photograph and all of you featuring in the next edition of the pamphlet of SPSTI. See, SPSTI is very grateful to Professor R.K. Kohli, who is our current president of the National Academy of Sciences Chandigarh chapter, and also the secretary, Professor Masin, who is also an emeritus professor at Punjab University. He is also with us. So we have a full house, all the office bearers with us, MIT University Vice Chancellor with us, staff with us, and everyone else around. And I am feeling thrilled. So I have already taken a lot of your time. So let me not stand more in between you and the speaker. Thank you very much. May I now invite Professor Apoorva Khare to come and deliver this lecture.
ये लो तार। नहीं ये और नहीं निकलेगा तो मैं इतने और कुछ
जीरो हो गया, आपकी जीरो हो गया।
ठीक है माइक के सामने अपने से आप बताइए
ये इधर से हटिए।
क्या करना वो प्रश्न एक बार अच्छा सिंगल ही करना
हाँ बहुत है बहुत दिख जाएगा सर। एक बार लिखना सर, कुछ भी लिख दो। एक बार राइट करना सर, एक बार।
बिल्कुल परफेक्ट नहीं, अभी मैं उसके आगे से निकला था ना, तो अब ठीक है। वो एक्चुअली ऑटो फोकस होता है, जैसे समझ रहे हो कुछ नहीं। हाँ जी, आप इस साइड से कर सकते हैं सर, इस साइड से फिर इस साइड से यहाँ से कर जाएगा। दोनों बोल सब सिंगल क्लिक करोगे तो हाँ। Okay, so I guess I can start. Let's start. Uh, I guess you can hear me. So, good morning. Echo हो रहा है. Echo हो रहा है. Okay, yeah. So, good morning, or maybe good afternoon. I don't know what the time is. So, yeah. So, I'm first of all. Thank you very much for the very kind introduction and the very warm welcome. And yeah, this is probably the biggest audience I've ever talked to about a topic that's something that I came up with जब मैं खुद क्लास 11 में था, जब प्रोफेसर ग्रोवर ने कहा कि there was a math Olympiad camp and so on. So I was one of the people in that math Olympiad camp. In fact, ISER Mohali, which is nearby, has two other professors in the math department who were with me in that math Olympiad camp. So I know some people for like 27 years we are still in mathematics. We are still solving problems and still enjoying mathematics. तो ये जो काम है, this was something that I was dabbling in in the summer after the math Olympiad camp when I was in class 11. And it's something which is very simple. It starts from something that we have all seen in school, and we will go explore what can be done beyond that. Okay, so this is about dividing numbers by other numbers, looking at how they are written. So for example, let's see if you can read this. Suppose I write down 143 and I ask, okay, should I step away? Okay, I guess you can see it. Does 3 divide 143? Right? So I think we all know the answer. We learned in school. What you do is you add up the digits 1 plus 4 plus 3. And then if 3 divides the sum of the digits, then 3 divides 143. Otherwise, it doesn't. Right? So यहाँ पे 1 plus 4 plus 3 is 8. 3 doesn't divide 8. So 3 doesn't divide 143. And the same question, the same test is true. We know if I replace 3 by 9, then 9 divides 143. Well, does 9 divide 1 plus 4 plus 3? No. So 9 doesn't divide 143. Right? What happens if I replace by 11? This is also a test that you would have seen in school. Right? And then the answer is, well, then you don't take 1 plus 4 plus 3. You take 1 minus 4 plus 3. You take the alternating sum and difference. Right? And now this is equal to 0. And 11 divides 0. Everything divides 0. 0 is a multiple of 11. So 143 is a multiple of 11. So this is a very simple test that we have seen in school. The question is why? And what more can you do? Okay, so why does it work? And okay, so maybe I should tell you why it works. And the reason, let's say that 11 divides 143 is the following. So what is 143? You would write this down as 3 plus 10 times 1 plus 10 square times, sorry, this is a 4, not a 1. 10 square times 1, right? The place value, units digit, tens digit, hundredths digit. Now, if you're dividing by 11, it's enough to write down, I can check, is there any other number that's differing from this by a multiple of 11, right? So I can say, well, if I subtract 11 times 4, okay, I don't get 143, of course, but what I can get is, if adding or subtracting a multiple of 11, if this number is divisible by 11, then so is the original one, because I've just changed it by multiple of 11. So dividing by 11 or not doesn't change. What happens here? You get 3, and now I can take 4 common, and 10 minus 11 is, so 1 times 3 plus minus 1 times 4. You see, so that's how the minus 4 aa jata hai. This 1 times 3 minus 1 times 4. 10 square is 100. 100 is 99 plus 1. So if I subtract minus 9 times 11 or 99 times 1, I get plus 100 minus 99 is 1 common. 1 times 1. So this is where I get the 1, the minus 1 and the 1. And this is the test for 11. So that's why I multiply this number by 1. I multiply this number in the middle by minus 1 and then by 1. And if this alternating sum is divisible by 11, it differs from the original number by some multiple of 11. So dividing by 11 or not doesn't matter. Right? So that's why the test works. So, and the same thing you can do for 10, for 9 and 3 is where all these 10s become 1s. So you can subtract 9 times 4 and 99 times 1. So these are all multiples of 9. The question was, what can you do beyond this? And so I was as I said, I was in class 11, coincidentally. I was looking at, like I was sitting in the summer at home and looking through some math books by, there was one author who was very popular. You might have seen the movie after her name, Shakuntala Devi. So she has written a lot of different math books. And one of those books, there was a test for 19. Let me tell you the test for 19. Okay. So how do you check if 19 divides some number? Let's say 361. Okay. And what she said was very interesting. She said, so over here, what we are doing is we are starting from the units digit, then the tens digit, then the hundreds digit. So we are going from right to left. What she said was, don't go from right to left, go from left to right. Okay. And multiply again 3, 6 and 1, not by 1 minus 1 and 1, but 1 minus 1 and 1 you can think of as 1 and then minus 1 and then the square of minus 1. This is the minus 1 power 0. This is minus 1 power 1 and this is minus 1 power 2. Don't multiply by powers of minus 1. For 3 and 9, you're adding up, so you're just multiplying by powers of 1. Don't multiply by powers of 1. Multiply by powers of 2. So the test, she said in her book, it's there in her book, is look at 3 times minus, so 2 power 0, that's fine, plus 6 times 2 power 1. You go from left to right. So the powers of 2 increase from left to right. Plus 1 times 2 power 2. And if this resulting number is divisible by 19, then the original number is divisible by 19. That is the test she had written in her book, which I read when I was, as I said, in school. So what is this number? This is 3 plus 15 plus 4 is 3 plus 12 plus 4 is 19. Certainly 19 is divisible by 19. Therefore 361 is divisible by 19. Okay. So that is the test that she gave. And then, so I was thinking to myself, we know it for 11, we know it for 3, we know it for 9. What we now know it for 19 as well. What about for 29? Or what about for 37? What about for 2023? Can one find a test that works for any number written in decimal base. Or you can also ask, what if I write it in binary? What if I write 361 in binary base? What if I write it in the computer base 16 that say computer programmers might prefer, hexadecimal base? So what kind of test, first of all, does such a test exist? And if so, is there a test that looks exactly like this, where you multiply the digits by the power of something, that something you determine based on what you want to divide by. So 19 ke liye, that something you multiply powers of is 2. 11 ke liye, you're using powers of -1. For 3 and 9, you're using powers of 1. What is the game? Can you find, if I say 29, can I find something whose powers I can replace here and then check whether it divides 20, is divisible by 29 or not? So that is what I was sort of doing. Okay, so let's see. So let's see so maybe I will ask here if somebody wants to guess it. So for 29, let's say I want to divide some number, let's say divides 89 or not, or maybe divides 87 or not. Okay, so I want to divide some numbers by 29. And the trick is there a game? Is there the same kind of trick that Shakuntala Devi said? Can you say that I take the first digit, multiplied by 1, and then the second digit, whatever, 7 or 9, multiplied by what? What is this number I should put in here so that this test works for any 2-digit number like this? If I want to divide by 29, can anybody make a guess? I don't know how conducive to guessing this format is. Any guesses? Anyway, so the point is this. So the way you want, the way you would guess it is as follows. I know that 29 divides 29. So if I want the same test, the same kind of test as Shakuntala Devi's to work, then I should just, one way to look at it is to test when 29 divides the test like this. The test I would get from this would be 2 times 1 plus 9 times what? And then what can I put here so that this number is divisible by 29 and therefore so is 29. And the simplest number you can put is 9 times 3, because 9 times 3 is 27 plus 2 is 29. So 29 divides 29 because, well, that it does. Let's check over here. So let's check for 87. I know that 87 is a multiple of 29, so that's why I took it. But now if you look at 8 times 1 plus 7 times the same number 3, what do I get? Well, I get 7 3s are 21, 8 1s are 8, add them up, I get 29. So 87 is divisible by 29 because 29 is divisible by 29. What about 89? If I put 9 here, 8 times 1 plus 9 times 3. I'm looking at powers of 3. So the first leftmost digit times 1, the next digit times 3. I get 27 plus 8 is 35. 35 is not divisible by 29 and therefore 89 is not. Right? So this test seems to work. Fine. So for 29 we found 3. For 19 we found 2. So let me tabulate. So now again, when you do science of any kind, mathematics is one of the sciences, right? So you should be, whenever you're doing experiments, you tabulate your findings, you record them. Right? So let's record our findings. And I did do that in school, when I was in school. A bunch of my summer was spent, it was very hot outside. So a bunch of my summer was spent with a notebook and an 8-digit calculator because we didn't have computers. We just had small pocket calculators and doing lots and lots of experiments and recording the subject. So let's say my D stands for the divisor. I want to divide by D. Okay. D equals divisor. Oops, sorry. This is going to be a weird thing. Fine. And I want to write down the constant, the number I multiply the powers by as K or K subscript D. This is the number that depends on D, and I will multiply the powers of that. Okay. So let's say, so for the 11, I will just say I had -1. So I subtract and add alternating. For 3 and 9, I had 1. But let me now write down some others. Let me write down 9. There was 1. 19, this was Shakuntala Devi. 9 is taught in schools. You multiply every digit by 1 and then you add the digits up. For 19, you multiply by powers of 2 and then you add the products. For 29, you have 3. And now this should tell you that there is some kind of a pattern that is waiting to be discovered. Now you can guess what, if I said 39, well, you would guess the obvious guess. And this should be 4. And indeed, 3 times 1 is 3, plus 9 times 4 is 36, gives you 39. So it is indeed conceivable that there is a test like this to divide by 29 or divide by 39. And that test exactly says multiply by powers of 3 or powers of 4. Okay? So, so the question now is fine. I see a pattern. First of all, I have to prove that this test actually works for 39 or it works for 29. But uske baad, I have to also understand why. Why is there such a test? And then even better, so given the evidence, first you have to explain your evidence. You formulate a hypothesis, explain your evidence. But then you have to, the other power of evidence or by science is, hopefully, it's not just to observe and understand what was done before. It is to predict. So can I now, if I give you say 47, or if I give you 1947, can you tell me what number is here? What is the power I should be multiplying by? Of course, if I ask you for 49 or 59, it's easy. You see the pattern. What about for something whose last digit is 7 or whose last digit is 1? So prediction and like your hypothesis, your model should be robust enough that you can use it to predict and accurately predict is what was a part of the proof. And in mathematics, that kind of accurate prediction is called proof, right? So we want to prove that such a model works. So that was basically the story that I'm going to tell you today, or part of the story. I don't know if I can cover the entire proof or something, but why does this test work? Right? That's the question. So roughly speaking, what happens is the following. Yeah. So let me just see. Sorry, and I should see the time somewhere. Okay. Actually, I should tell you. So many years later, when I was in, I think I had maybe just joined IISc already as a faculty. So this is more than 20 years later. I got an email from somebody in England. Oh no, actually, I didn't get an email. I saw in the papers, in the newspaper, somebody in England, a Nigerian born UK schoolboy called Chika Ofili, he discovered the test for 7. Yeah, and so there's another test. Since I asked about 1947, let me just tell you about the test for the 7 part of it. For 7, he discovered essentially that what you have to do is multiply by powers of 5. That's what he discovered. Okay, so the question really was, so, but okay, so eventually when I found out what is going on, and later on somebody else told me. So what I was discovering, what I discovered in school, what Shakuntala Devi told in her book, in her all the tests that we see in our school itself, 11, 3, and 9. So all these things are part of, and what Chika, the school child in UK discovered, all of these are part of. These were sort of known to people in ancient India. And so this test, he will appears in Vedic mathematics. And the name that they mention there is called the Eka Adhika. So this K is what they call as the Eka Adhika. Maybe it's better to just mention it in Hindi. Ekadhik. Ekadhik means one more than. So one more than what? What is one more than what over here? So the idea is the following. Okay, so let me write down, let me erase some of these things. So the Ekadhik is basically the following. And so what all of us were doing, we were basically rediscovering this fact that was known to ancient mathematicians in India. This is not something very deep, as you will see, but it is still a new fact. If you haven't seen a test for 9 or maybe 29 before, then that might be surprising. And so now, of course, in the Math Olympiad camp, if you attend one of those, you learn how to explain all of this. But unless you have seen that kind of mathematics, this is not something that is taught in schools. Okay, so Ekadhika basically says the following. Look at which multiple of 10 remember, we are writing all these numbers in base 10 in decimal representation. Right? So, what is the smallest multiple of 10, which is ek adhik than the multiple of this divisor? So, 10 times k minus 1 is a multiple of the divisor d. K is this kd. This is the point of ekadhik. So, for example, 10 times 2, 10 times 1 is not a multiple of 19 plus 1, but 10 times 2 is 20, 20 minus 1 is 19. 10 times 3 is 30, 30 minus 1 is 29. 10 times 5 is 50, 50 minus 1 is a multiple of 7. And you can check that 49 is a multiple of 7, but 39, 29, 19 and 9 are not multiples of 7. So the smallest multiple of 10, which is one more than a multiple of 7, is exactly 5. And that is why that number is 5. That is why this number is 2, 3 or 4. So this is how you calculate. So this is the model. This is the hypothesis that you must now verify or you must prove. And the point is there are infinitely many numbers to divide by. So you can't verify infinitely many calculations. This is where the power of a proof comes in. It's in mathematics. We don't verify something empirically for infinitely many numbers. We prove it. We try to prove something. Right? So you have to explain why. So if you have, for example, in school, you would see these SAS congruence axiom and the SSS congruence axiom, and the AAA is not a congruence axiom because AAA says that it's a similarity. So AAA, if two triangles have the same angles, then they don't need to be congruent. One can be a blown up or shrunk down version of the other. But if they have the same sides, they are congruent. Two sides and the angle in between, they are congruent. So this kind of thing, right? So just like that, and then you explain, somebody asks you a statement in high school geometry, you write down statement, reason, and you go down and you explain the statement you want to prove using the reasons and the axioms you have. So that's the kind of thing we have to do for explaining this. And that's what, but the answer is exactly this. The answer is why 5? Because 5 is 5 times 10 is the smallest multiple of 10, positive multiple of 10, which is one more than the multiple of what you want to divide by. So that's this is really the divisibility test for any number. Let's say any number co-prime to 10. When you write it in base 10, what if I was writing it in base 12? If I'm writing it in base 12, suppose we all have 2 extra thumbs or 2 extra fingers, then maybe we would be counting in base 12. In that case, I would just change the 10 to 12. That's all. So that is the divisibility test for any number, to divide by any number when you write in digits in any base. Since we work with base 10, we have 10 fingers, so we write down 10 times k minus 1. And that is how you would calculate the ekadhik. Okay, so that's the test. Now, why does it work and how do you show that it works? As I said, you can't verify something for infinitely many calculations in finite time. But this is where the power of variables comes in. So let me switch tracks just for 2 minutes and remind you that why the power of variables is very important in mathematics. Right? So suppose somebody tells you that let me multiply two odd, so I can take 2 consecutive odd numbers and I multiply them and let me add 1 to that. I will always get a perfect square. Now that might sound mysterious and if you have not seen this before. So let me say I take 5 times 7, I add 1 and I get exactly 36, which is 6 square. I take 11 times or 9 times 11, I add 1. I get, well, 99 plus 1 is 100 and 100 is 10 square. And I'm telling you that this is always going to happen. Right? So now if you, oops. Good. So while we wait for it, the microphone is still working, is it? Chali. Is the mic working still? Yeah. Okay. So how would you prove, how would you, like understand something like this? You can, of course, keep trying to do every calculation, 133 times 135 plus 1 and keep going. So, of course, you can try and do all that, but that is sort of very, that is not going to get you to understand the phenomenon. It's not going to give you an understanding of why it works. All you will see is how it works for 133, how it works for 9. But the moment you use variables, then suddenly these individual statements, which could be verified individually using some computing time of your calculator, you can verify them all at once in one calculation. And the calculation is much simpler than doing 133 times 135, right? What do? All you do is you say, well, I have to add two odd numbers, or well, I have to multiply two numbers which are consecutive odd numbers. It's the same as saying I have to multiply two numbers which differ by 2. So let me write the middle number as, let's say, n. Okay. Then what is the lesser number? The lesser number is n minus 1. The bigger number is n plus 1. And I don't care what n is. N can be 2, then I do 1 times 3. N can be 134, then I do 133 times 135. I don't care what n is. N is some number. All I know is it's an integer. It's a counting number. Okay. I multiply n minus 1 times n plus 1, and I think everybody in school has seen this, right? You can multiply by using whatever, associative, distributive law, and so on. So you get n minus 1 times n, which is n square minus n. And then plus 1 times, sorry, n minus 1 times n and n minus 1 times 1 plus n minus 1. And now whatever n is, whether n is 132, whether n is 5, I don't care. This n and this n cancel because you're subtracting and adding the same amount. It doesn't matter what that amount is. And that is the power of variables. What you get here, sorry, and I'm supposed to add a 1. Let me add a 1. So this minus 1 and plus 1 also cancels. And all you get directly is n square. Right? So without doing infinitely many calculations, I have understood infinitely many calculations using the power of variables. So there are some very powerful ideas in mathematics. This is probably, I don't know, this is probably the most powerful of them really at this level. Is once you know how to use variables, then you can understand infinitely many calculations. You can carry them all out. And what this tells you also is the fact, I told you that the product of two consecutive odd numbers plus 1 is a square. But I never said anything about what this n is. N can be odd, n can be even. So in fact, this tells you that the product of two consecutive even numbers plus 1 is also a square. For example, if you take 4 times 6, right? You could take 4 times 6 plus 1. These are not odd numbers, these are even numbers. But when you add them up, you get a square. I could take 10 times 12 plus 1. 121 is 11 square. So just using variables, sometimes you can even remove sort of unnecessary assumptions like odd hai, even hai, kya hai. It's a number. Multiply the number minus 1 times number plus 1, add 1, you get the number square. And not only do you understand it's a perfect square, you understand of what number it is a perfect square. It is a square of the middle number. If you take odd numbers or even numbers, either way, if they are differing by 2, then the square that you get is the square of the number in between. So this is the power of variables. And when you want to prove something like a divisibility test for infinitely many numbers, you should be using variables. And this is generally what happens in all of mathematics. Once you try to prove something, we typically try to prove it for infinitely many things at once. And when we do that, that is when variables very naturally come in, because you can use them so powerfully and verify infinitely many calculations in one calculation, in one stroke. Okay, so that's how you take numbers. Okay, so fine. So let's get back to divisibility tests. But I hope I sort of made the point that, yeah, using variables is helpful. So now let me maybe show you why, let me work out why 361 is divisible by 19 if you can use the 2 test of Shakuntala Devi. Okay, let's try to work that out and see what is being used. And then the idea will be exactly the same, to abstract the part, that is to distill the part that you want to use in terms of the variables in some sense. We will replace 2 by k, we'll replace 19 by d, and we will say that something divides, so d divides 361 if and only if that happens. Okay, so let's write down 361. So 19 divides 361. I'm going to state something which sounds very mysterious to start with. Okay. If and only if we in mathematics, we use this symbol for saying if and only if 19 divides. Oh, we get this again. We can wait. If and only if 19 divides 4 times 361. Okay, why? Of course, if 361 is a multiple of 19, then 4 times that is also a multiple of 19. That is obvious. The question is why, if 19 divides 4 times this number, does 19 divide the number? And that is because 4 has no common factors with 19. 19 is a prime number. If 4 times something divides 19, is a multiple of 19 and 4 is not, then this must be a multiple of 19. That's also a very powerful idea. It's called the unique factorization of numbers. Okay? Meaning that every number can be written as a product of prime numbers, and you have some prime number, it has to be part of that product. Otherwise, it will not divide the bigger number. Okay. So now, why did I say 4 times 361? I said it because what I'm doing is the following. Let me now write down 4 times 361. So it is, let's see, 1. So 3 times 10 square times 4, which is 4 is 2 square, plus 6. This 4 times 361, I'm expanding. 6 times 10, and I have to multiply by 4. So let me, 4 I'm splitting into 2 2s. One of the 2s goes here, and one of the 2s goes here. Okay, fine. Here the 2 square actually goes with the 10 square. However many 10s you see, those many 2s you keep, and the rest of the 2s you multiply by the digit. So let me actually change the 2 square here. Good. And then plus 1 times now there is no power of 10, right? This is a units digit. So I don't multiply by 10 here, I multiply by 2 square here. Okay, now let's look at this calculation. So I'm going to replace 10 square and 2 square by this. So I'm writing this down as 3 times 20 square, and 20 is a multiple, is 20 is, so 2 is the ekadhika. So 20 I will write down as 19 plus 1. Okay, plus 6 times 2 times 20, and then plus 1 times 4. Okay, so this is the calculation I have. And what the test by Shakuntala Devi said what? It said that 19 divides 361 if and only if 19 divides the 3 plus 6 times, let's see. We wanted to say 19 divides 361 if and only if 19 divides 3 plus 6 times 2 plus 1 times 4. Okay. So now this is where we are basically getting there, right? So the step is there is a, this is going to go, this is what we want to prove. We are saying this is true if and only if, let me go through a slightly longer path. 19 divides 361 if and only if 19 divides this, 4 times 361, which was equal to 3 times 19 plus 1 square plus 6 times 2 times 19 plus 1 plus this. And now here I see I can subtract 4 times 361 minus any multiple of 19. Right? And you can now see that there are going to be a multiple of 19. I'm going to subtract. I'm going to subtract 19 square times 3 plus 2 times 19 times 3. I will be left with 1 square times 3. Right? So what I will be left with is if I subtract 19 square plus twice 19 times 3, And similarly here I subtract 6 times 2 times 19. Then what do I get? This is exactly 3 times 1 square plus 6 times 2 times 1. If I subtract this multiple of 9 plus 1 times 2 square, 1 times 4. So let me remove the one part. Right? And so this is exactly the test that Shakuntala Devi gave. And the idea is exactly that since you have a Ekadhika, 90, so 2 is the Ekadhika for 19. So when you write down powers of 10 multiplied by the same power of 2, you're really getting a multiple of 19 plus 1. And every such multiple of 19 plus 1 square or cube or fourth power, all those leave a remainder of 1 when you divide by 19. So subtract that relevant multiple of 19 and you just get powers of 1 every single time. And so you get 3 times 1, 6 times 2, 1 times 4. And that is exactly the test that Shakuntala Devi gave. And once you realize that this is what it is, then you can do the same calculation with 29 and 3. I could have done 29 here throughout and put in a 3 here throughout and check that exactly the same thing holds, replacing 2 by 3 and 4 by 9. And so that's the kind of calculation that goes into proving this divisibility test. And again, so basically you have to identify what is necessary and what is not. The fact that this was 19 was necessary only to the point that this was a 2. If I change this to 29, I have to change this to a 3. If I change this more generally to a D, if I was writing this 10D is a multiple of D, so if I change this to a D instead, divides 361, then I would have to say, well, D divides, I wouldn't say D divides 4 times that, sorry. I would say D divides 2, what was 4 here? 4 was 4 was 2 square. 2 was the Ekadhika. So here I would say D divides KD square times 361. Now here I would say this is 10 square times KD square. This is the KD here and the KD here. And this is KD square here. So you have to just understand what is the relevant part, sorry, and what is not. So if it was 19, then you see a 2. If it's a 4, it's the power of 2. So whenever you see any general base like 29 or 39 or 1947 or 7, that was what that school kid in the UK proved, you would replace that over here and you replace the correct value of KD here. You would put 5 here. And so once you understand which part of this calculation really uses 19, well, it only uses 19 because it uses 4. Once you change 19, you change 4, automatically the whole thing, the whole proof goes through. And so this is how you would prove something in general for any, and this was the part about the 19. Now, similarly, you could generalize it to the base as well. If you wanted to do it in base 12, well, you would replace all the 10s that you see here by the base 12. Now, in base 12, the Ekadhika for 19 will no longer be 2. The Ekadhika for 11 will no longer be minus 1. But so that's what you have to change. Once you change the base, then you change the, and you have the divisor, then you change the Ekadhika value. And so you have to do it very carefully. Which one should be changed first? Which one is depending on what else? But that's the idea behind this divisibility test for any number in any base. It is that you multiply from left to right by a power of the specific k, such that 10k minus 1 is a multiple of d. Okay. I should, of course, point out before I finish that, that this is only true for numbers that are whose last digit is 1, 3, 7, or 9. These are numbers which are co-prime. Okay, so like I told you, it's a test for 11, it's a test for 7, it's a test for 19. But why only numbers that are ending with 1, 3, 7, or 9? Right? And that is because these are precisely the numbers that are co-prime to the base 10. So D ending in 1, 3, 7, or 9 are the numbers which have no common factor. What are the factors of 10? 2 and 5. So if it ends with 1, 3, 7, or 9, it's obviously odd. So it cannot have a factor common of 2. And since the last digit is not 5 or 0, it's obviously no factor of 5. So there is only the ones which are divisible by 1, 3, 7, whose last digit is 1, 3, 7, or 9. For those numbers, this test would work. So you can ask why? Why does this test only work for those numbers? Why not for anything else? Because if you try to do this for test dividing by a number by 2, and you try to understand what is the eka adhika for 2, you want a number if d equals 2, right? Can such a test work for 2, where you multiply from left to right by powers of some number? Well, the problem is the following. When you have this for 2, you want to ask if what is the eka adhika for 2? What is kd? Maybe I should erase the question here and ask the question here. Does there exist such a number kd for 2? K for 2? Well, that would mean you would like to have 10 times k minus 1 is a multiple of 2. So for what integer, for what all possible integers is this true? So for what is one value of k for which this number is a multiple of 2? And the answer is there is no such number, right? Because this is a multiple of 2. This is an even number. If this is even number, then minus 1 becomes an odd number. Odd number is not a multiple of 2. So you can never have a divisibility test for 2 or similarly for 5 of this kind, because 10k minus 1 is also a multiple of 10k is a multiple of 2 and of 5. When you subtract 1, it will never be a multiple of 2 or 5. So such a number can never exist. So you can not just prove positive results using variables, but just by observing this simple fact, you can prove negative results, that sometimes something can never happen. That's a proof that the test for 2 cannot work like this. The test for 5 cannot work like this. That's because you just know basic properties that multiple of 2, a multiple of a multiple of 2 is still a multiple of 2, right? So this is how you establish findings, I guess, in mathematics. You prove things, right? And so there are positive proofs, like here is a test. There are negative proofs. So certainly if you want to divide by 2 or 5, even if I want to divide by 8, let's say I want to divide by 8, then I would want some number like this, which is a multiple of 8. Can that happen? Again, no, because every multiple of 8 is even. And this number is even, so the full thing is odd. So this number can never be a multiple of 8. Right? So that's why whenever you have any power or any multiple of 2 you want to divide by, or any multiple of 5 you want to divide by, you can never have a test like this. So really what you want are the only numbers for which such a test could occur. I'm not saying it always does. The only numbers for which such a test could work is the ones ending in 1, 3 or 7 or 9 in the unit space. So the last thing to say is why, suppose a number does end in 1, 3, 7 or 9. Suppose it is co-prime to 10. Why for that number does this number always exist? The entire test is based on such a number existing. Provided there is a ekadhika, provided there is a k such that 10k minus 1 is a multiple of say 19, or 10k minus 1 is a multiple of 35, not 35, 37, or of 1947, then you can run the test from left to right. So for 19, Shakuntala Devi checked that 10 times 2 minus 1 is a multiple of 19. For 29, we can check. Again, for individual numbers, we can check that if they are co-prime to 10, this is true. But I don't want to keep checking infinitely many numbers, infinitely many co-prime numbers. So again, you have to ask, is there a proof? Is there a way to write down in one stroke the fact that whenever D is co-prime to 10, there is some number k such that 10k minus 1 is a multiple of D. How does one write this down? And the answer is you can write this down. And let me just conclude probably in the last few minutes by telling you what the answer is. So, okay, I'm actually going to be cheating because I will use a fact that I will not prove. But this fact is probably known to everybody here. Now, if you ask me why this fact holds, then I won't be able to tell you so quickly. But this fact holds that if you have two numbers, I said that D is co-prime to 10, D co-prime to 10 to the base 10, right? How does one write this down? Another way to write this down is to say that the GCD, the greatest common divisor, or maybe you call it the HCF, the highest common factor of D and 10 is equal to 1, right? That's what co-prime number. There is no other integer number that divides both D and 10 if they are co-prime than 1. The only positive number dividing them both is 1. Then -1 also divides it. But when two numbers have GCD equal to 1, there is a fact, and this is the part where I'm cheating. You probably know this fact, but I'm not going to give you a proof of this fact, that this happens if and only if you can find numbers. There are numbers P and Q, or let's say maybe I'll call them M and N, integers, such that D times, sorry, let me say K and M and K. Let me call it K for the obvious reason, such that D times M plus 10 times K equals 1. I'm not saying that these numbers are positive. Of course, they're not positive, because then you get something bigger than 1. But let's say there is a number, M is negative, K is positive. So D times M plus 10 times K is 1. Whenever the number is co-prime to 10, meaning its last digit is 1, 3, 7, or 9, the GCD is 1. Therefore, there are these two numbers. Some integers exist. What are these integers? I don't know. But we know from school that such integers always exist, right? And D times M plus 10 times K is 1. But what does that mean? It means that 10K minus 1 is equal to, I can take D on the other side, minus D times M is 10K minus 1. And so you see that there is a number K such that 10K minus 1 is a multiple of D. That is exactly what we need for the Ekadhika. Once you have that number in hand, then the entire test goes through in a manner where you just generalize what I wrote down here. You can generalize what I wrote down here to work for any number in any base, any divisor. But the reason for the test even starting, the first thing is the test should start. The test should start meaning this number should exist, K. This number exists because of this reason. Because we've seen in school that, when you have two numbers being co-prime, having no common factor, you can find two other integers such that they add up this way. And that is why the Ekadhika exists. Then once you have that Ekadhika, you can basically carry out this test. And that was essentially what I did in school. I looked at Shakuntala Devi's answer, that is the test. And then I had to reverse engineer and understand, okay, can I get more data for other divisors for 29, 39? And then once you get that, can you spot the pattern? And once you spot the pattern, you have to prove it. And then once you prove it, that's the test. Okay, so I think this is a good point to stop. So thanks again.
So thank you so much, Dr. Apoorva, for this wonderful talk. I'm sure that I speak on behalf of everyone who has had the privilege to listen to such an enlightening and easy to understand insight into the world of mathematics. I would now request Professor Kuldeep Bhasin, Fellow of National Academy of Sciences and NASI Senior Scientist, former Dean of Faculty of Sciences, Emeritus Professor Chemistry, Punjab University, to kindly give the vote of thanks. Welcome, sir.
Okay. Yeah. Good afternoon, ladies and gentlemen. I take this distinct opportunity in expressing my heartfelt thanks to Professor Apoorva Khare, a highly accomplished mathematician decorated with Swaran Jayanti and Ramanyan Fellowship and recently 2022 Bhatnagar Award for his highly informative, inspiring, and scintillating talk. Mathematics, I learned, is considered as the mother of all sciences because it is a tool which solves problems of every science. I fully agree with Professor Apoorva Khare's views that he has shared with the magazine Hindu that today's mathematics is not only necessary but pervasive in daily life. I'm sure that you all will agree with me that Professor Apoorva Khare has painted a state-of-the-art presentation on the canvas with his today's lecture on divisibility test, one test to fit them all. This lecture was organized in a hybrid mode, and I would like to mention that his take-home message is very clear and loud. I may add that today's being a very special day, National Mathematics Day, Professor Karge has left no stone unturned in devising a very descriptive this talk. Please join me in passing a hearty vote of thanks with big applause to the highly accomplished and profoundly decorated mathematician. I'm extremely thankful to Professor Kohli, Vice Chancellor, MIT University, Punjab, Mohali, and Chairman, Chandigarh Chapter of NASI for presiding over this memorable lecture, which is fourth in the series being held at MIT campus, Mohali, to mark the birth anniversary of great Indian mathematician. This lecture is being organized by Chandigarh Chapter of NASI, National Academy of Sciences, Allahabad, in association with the Society for the Promotion of Science and Technology in India, Chandigarh chapter of INSA, and INEAS, New Delhi. I'm thankful to Mr. Dharamveer, who is unfortunately not present here. IAS retired Professor Arun Kumar Grover, President and Vice President, respectively, of SPSTI, Society for the Promotion of Science and Technology in India, in arranging this outstanding lecture on National Mathematics Day. I'm grateful to Dr. Swati Tyagi, Head of the Mathematics Department, Professor Simran Tandon, Program Officer, Mr. Dilip Kumar, Registrar, MIT University, officials of IIT, Cell, Colonel Amrit Gotra, Director Operations, and the supporting staff for their untiring efforts in giving a concrete shape to this program. Special thanks are due to Professor Mrs. K.R. Dharamveer, General Secretary, and Mr. Mahipal, Coordinator, SPSCI, for organizing this event in a very sophisticated and befitting manner. On behalf of NASI, SPSCI, INSA, INEAS, students and colleagues of MIT University, and online presentees, I'm indebted to Professor Khare for being with us this morning and enlightening us with all his scholarly and mesmerizing talk. Thank you very much, Professor Khare. Thank you.
I would now like to